Hello everyone, welcome to the sixth lecture of our module 4, that is moving loads and influence lines. So these are the contents of our presentation: maximum shear force and bending moment due to moving loads, and which include the topics that is single point load moves across the span, then UDL longer than the span moves across the span, then UDL shorter than the span, and the problems related to the above topics. Okay, so before moving on to the topic, I want to give you an introduction, which we discussed in the previous section. So the lines that represents the variation of responses at a given section with motion of load is called influence lines. And also the influence line diagram is a diagram whose ordinates, which are plotted as a function of distance along the span, give the value of an internal force like a reaction or a shear force or bending moment or a displacement at a particular point in a structure as a unit load moves across the structure. Okay, so you know influence line diagram, and you already know how to draw the influence line diagram for shear force and bending moment of a simply supported beam. Okay, so first topic is the maximum shear force and bending moment due to moving loads. Okay, so a designer always want to find the values of maximum shear force and bending moment at a given section C when the load moves from left to right of the beam. Okay, that means where to place the load to get the maximum value and also the maximum value of shear force and bending moment. And also we have to find the absolute maximum value of shear force and bending moment. So the absolute maximum value means the maximum of maximum shear force and bending moment. Okay, so these are the following types of loads on a simply supported girder that we are going to consider. That is a single point load, then UDL longer than the span, then UDL shorter than the span. Okay, the train of point loads will be discussed in the next section. So see this figure. When the load at this section C, you will get the maximum ordinate of bending moment, and that ordinate is equal to Z into L minus Z by L, and that into just multiply the maximum ordinate into load, that is W Z into L minus Z by L will give the value of maximum. See, the negative shear force ordinate is maximum when the load is at Z is equal to L and the value is W. That is 1 into W. Okay. Then the maximum shear force ordinate is 1 when we place the load at Z is equal to 0. That means here. So the value is just multiply the ordinate, that is 1 into the load, that is 1 into W, that is equal to W at the point A. Okay, so this is a figure for the maximum positive shear force, and this is a figure for maximum negative shear force, that is when Z is equal to L, and that is when Z is equal to 0. Okay. Then coming to the absolute maximum value of bending moment. It is when we place the load at the midpoint of this beam. That means when the load appears at the midpoint of the beam, that is when Z is equal to L by 2, you will get the value of absolute maximum bending moment. Okay, just use Z is equal to L by 2 in the equation for maximum bending moment. Okay, that is W into L by 2 into L minus L by 2 divided by L, that's equal to W. L by 4 is the value of absolute maximum bending moment for a simply supported beam with point load moves across a span. Okay. Then coming to the next topic, that is simply supported beam with UDL longer than the span. So here you can see a simply supported beam. The ends are A and B, and consider a section C at a distance Z from the left support A, and the intensity of UDL is W kilonewton per meter, and the total length of the beam is L meter. Okay, consider that this UDL is moves from A to B. Okay, then you have to find the maximum negative shear force, maximum positive shear force, and also the maximum bending moment. Okay, so let's see what will be the maximum negative shear force. Just draw the influence line diagram for the simply supported beam with UDL. So that the condition is that when the right end of the UDL is at the section C, then you will get the maximum negative shear force. So place the right end of the UDL, that means the head of the UDL at the section C. So the remaining part will appear on the span AC. That means the negative shear force is maximum when the UDL occupies the portion AC only. That is the head of the UDL is at section C. So the value of maximum negative shear force is equal to the intensity of load into area of influence line diagram for shear force for the length AC. So in the case of a point load, just multiply the ordinate into load. In the case of a UDL, we need to find out the area of this shaded portion that comes under this UDL, and that into intensity of load will give the maximum negative shear force. So here you can see a triangle on which the base is Z by L and the height is Z. So just find the area of this triangle, that is half into Z by L into Z, and that into W will give the value of maximum negative shear force, and that's equal to W Z square divided by 2L. Okay. So that's about maximum negative shear force. Then maximum positive shear force when the tail of the UDL is at the section C. That means when the UDL is in the span CB only. So here you can see the tail of the UDL is at the section C, or the UDL is covers the span CB only. Similar to the previous, just find the area of this portion under this UDL. Here also you will get a right angle triangle. And how will you find the area of this triangle? That is half into B into H. Here, so here the length is L minus Z and the ordinate is L minus Z by L. That into half into W. So that's equal to W by 2 into L minus Z the whole square divided by L. So that's a max value of maximum positive shear force. Okay. Then coming to the maximum value of bending moment. So that appears when the UDL covers the entire span. So place the UDL in the entire span. So the length of the beam is L, or the length of this UDL or the shaded area is L. Just find the area of this triangle, that means half into L into Z into L minus Z by L into L. That means the intensity of load. You will get the maximum bending moment at the section C. So that's equal to W by 2 into Z into L minus Z. Okay. Then next we have to find the absolute maximum value of negative shear force, positive shear force, and also bending moment. So negative shear force is maximum similar to the case of point load. At Z is equal to L, the ordinate is 1. So when this ordinate is 1, you will get the maximum value of negative shear force just by taking the area of this triangle and that into the value of load. That is W into half into L into 1. That is WL by 2 is a value of absolute maximum negative shear force. Okay. So that is the absolute maximum negative shear force occurs when Z is equal to L. Okay. And also the absolute maximum positive shear force occurs when Z is equal to 0. That means at the end, at the point A. So place a UDL for the entire span and just find the area of this shaded portion. That is half into L into 1 into W. That's equal to WL by 2. So the absolute maximum positive shear force and also the maximum negative shear force is equal to WL by 2. Then coming to the absolute maximum bending moment. So it is occurs when Z is equal to L by 2. Just substitute the value of Z is equal to L by 2 in the equation for maximum bending moment. So that's equal to WL square divided by 8. Okay, and it occurs at the midpoint of the B. Coming to the third case, that is a simply supported beam with UDL shorter than the span. So here you can see a simply supported beam of length L, and here also consider the section C at a distance Z from the left support, and also the length of the UDL is D, and also the intensity of load is W kilonewton per meter. So consider a simply supported beam with a length L and on which a UDL of intensity W per meter of length D moves across the span, or it moves from left to right over the beam. Okay. Then, similar to the previous cases, we have to find the values of negative shear force and also the positive shear force first. So, the value of negative shear force occurs when the head of the UDL reaches the section C. That is, when you have to place the head of the UDL at this section C, and the remaining part will appear the span AC. Okay, so here you can see the area under this UDL as a triangle. So just take the area of this triangle and that into intensity of load, you will get the maximum negative shear force, and that's equal to W L Z square divided by 2L. Okay, so this is the diagram for influence line diagram for maximum negative shear force. Then the maximum positive shear force. So it occurs when the tail of the UDL is at the section C. So you can place the tail of the UDL here, and the remaining part will appear in the span CB. Okay, so let this ordinate as L minus Z by L, and we can name this ordinate as Y1. So by using the property of similar triangles, just find out this ordinate Y1 here. So here you can see a trapezium. So find the area of this trapezium by using the equation half into H into A plus B, where H is this side and A and B are the parallel sides. So the maximum positive shear force is equal to W, that is the intensity of load into area of this trapezium. Okay, so W into half into D into L minus Z by L plus Y1 is the maximum positive shear force. So this is the influence line diagram for maximum positive shear force. Okay, the value of H, just place the UDL at a distance H from the section C, and the remaining part will comes in the span CB. Okay, so that's a condition for maximum bending moment. So here you can see the area covered by this UDL. So this is the ordinate Y1 and this is the ordinate Y2. Okay, so here you can see two trapeziums. So find out the area of this trapezium, and also the another condition is that the ordinates y1 and y2 should be equal. The ordinates y1 and y2 should be equal. Okay, so these are the conditions to get the maximum bending moment, and just find the area of that shaded region, and that into W will give the value of maximum bending moment. Okay, then coming to the values of absolute maximum negative shear force when the ordinate is 1, that into the area of the intensity of load will give the maximum negative shear force, and similarly maximum positive shear force. Then coming to the absolute maximum bending moment, for absolute maximum bending moment the ordinate YC should be maximum, that is when the UDL should be placed on such a way that the midpoint of UDL should be at the midpoint of the beam. Okay, the load position is to be such a way that the section divides the load in the same ratio as it divides the span. Okay, so the load should also placed at the midpoint of the beam. Okay, that means the center of gravity of load would be at the midspan. So that's a condition for absolute maximum bending moment. Okay, so these are the theories behind this. Next, we have to see the problems related to this topic. So, problem number 1. So, this is a question. A simply supported beam has a span of 15 meter, a UDL of 40 kN per meter and 5 meter length crosses the girder from left to right. Draw the influence line diagram for shear force and bending moment at a section 6 meter from left end and calculate the maximum shear force and bending moment at this section. Okay, so here in the question it is given that the length of the span is 15 meter. So L is equal to 15 meter. Then the intensity of UDL, that is W, is equal to 40 kN per meter, and the length of the UDL, that is D, is equal to 5 meter. So the length of the UDL is less than the length of the beam. Okay, and also section C is at a distance of 6 meter from the left end. That means Z is equal to 6 meter. So first of all, draw the influence line diagram for shear force and bending moment. So this is a influence line diagram for shear force and this is a influence line diagram for bending moment. Okay, now the ordinate, that is here the ordinate is L minus Z by L and here the ordinate is Z by L. So here I marked it, it's a wrong, that is it's just L minus Z by L is there. Okay, so and that's equal to 0.6 and Z by L is equal to 0.4. And the influence line diagram for bending moment, that's a maximum ordinate is Z into L minus Z by L and that's equal to 3.6. So these are the figures. Then next we have to find the value of maximum negative shear force. It occurs when we place the head of the UDL is in the section C. So place the head of the UDL at the section C, find out the area under this UDL. So here you can see it is a trapezium. So just find out this ordinate by considering the similar triangle properties. That is, this length is 1 meter, that is the total length of the UDL is just 5 meter. So the remaining 1 meter is here. So 1 divided by y1 is equal to 6 divided by 0.4. From that, y1 is equal to 0.067 meter. So the maximum negative shear force is equal to intensity of load into area of that trapezium, and that's equal to 46.67 kilonewton. Okay. So next thing we have to find is the maximum positive shear force. It occurs when the tail of the UDL is at the section C. Okay, similar to the previous case, here the ordinate is y2. So just take the property of similar triangles. So here the total length of the span CB is 9 meter. So the length of the UDL is 5 meter. So the remaining length is 4 meter. So 0.6 divided by 9 is equal to y2 divided by 4. So that y2 is equal to 0.267 meter. From that, the maximum positive shear force is equal to 86.7 kilonewton. So you got the values of maximum negative shear force and also the maximum positive shear force. Then you have to find the value of maximum bending moment. So therefore that there is a condition, that is H by D is equal to Z divided by L. That is H divided by 5, that is the length of the UDL, is equal to 6 divided by total length of the UDL. From that H is equal to 2 meter. So place the 2 meter of the total length of the UDL on the left of the section C and place the remaining part on the right of the section C. That means 2 meter comes here and the remaining 3 meter will be comes here. Just mark the shaded area. Just find the area of this shaded area and also find out the area that into the intensity of load will give the value of maximum bending moment. So here you can see the two trapeziums. By finding this ordinate by taking the property of similar triangle, that means 3.6 divided by 6 is equal to y divided by 4, which implies y is equal to 2.4 meter. So that the maximum bending moment is equal to 40 into half into 2 into 2.4 plus 3.6 plus 40 into half into 3 into 3.6 plus 2.4. So the total is equal to 600 kilonewton meter is the value of maximum bending moment. Okay. The problem number W is Z square divided by 2L. So W is equal to 2, that into Z is 8. So 2 into 8 square divided by length of the UDL is just 25 meters. Okay. Now, so this is a figure for the maximum positive shear force. Just place the tail of the UDL is here. Then find out the area of this triangle below this UDL. Okay. So the maximum positive shear force is equal to W by 2 into L minus Z the whole square divided by L. So that's the equation. Just substitute the values in the equation for maximum positive shear force, and that's equal to 11.56 kilonewton. Okay. Then coming to the value of maximum bending moment. It occurs when the UDL covers the entire span, and find the area of this shader region. So the area of the shader region, that means the area of this triangle. And that's equal to WZ by 2 into L minus Z is the equation. So W is 2, Z is 8, and L is 25. So that's equal to 136 kilonewton meter is the maximum moment at section C. Now coming to the absolute maximum bending moment, and it occurs when the UDL is in the midspan, that is Z is equal to L by 2. So the equation is WL square divided by 8. That means when a simply supported beam carries a UDL for the entire span, the absolute maximum bending moment would be equal to WL square by 8. And that's equal to 156.25 kilonewton meters. So hope you're clear with these problems, and thank you for listening. Thank you.